I loved reading this work. I love the catalytic resonance theory, and it's one of those things where I'm like, I need to sit down and do the math so it makes more sense to me. But I understand it. But yeah, I've got your paper right here. So
nice.
It was a good read.
Glad you enjoyed it. Yeah, the easiest way to explain it is you're changing these potentials, which is like changing temperature in thermal catalysis. You're trying to balance your kinetic rate constant and your coverages. You can never find one condition that properly balances them both. So you're oscillating between conditions that satisfy kinetics and thermodynamics at a time scale which lets you maximize both. So I think in our case, we knew there was a lot of complexity associated with understanding these dynamic catalyst systems. We wanted to do it with a precious metal like platinum because our goal was to show that through dynamic oscillations, you can exceed some of the best static catalysts. So that's why we chose platinum. And to avoid complexity, we wanted to work with just bulk platinum to avoid support effects and things along those lines. The challenge with that has been that you have very low surface area of exposed platinum. So if you were to use something like a thermal conductivity detector to quantify the CO2 that's formed in the course of formic acid oxidation, which we chose as a model reaction, it would be almost impossible, if not just highly inaccurate, to try and quantify CO2 with the thermal conductivity detector, given the low surface area of bulk platinum. And again, we want to avoid supports which could disperse the platinum because we didn't yet understand what role the support was going to have.
And so when you say bulk platinum, this was like a mesh of platinum? I actually didn't.
Even simpler, just a platinum wire, just a thin
wire. Yeah.
Just a wire of platinum.
Oh, that makes sense. Well, let's go ahead and we can get started from the beginning because we're going to cut this up and post it if you're okay with us posting. We'll send it to you beforehand so you can approve it. But I'm here today with Omar Abdelrahman talking about his work on resonance promoted formic acid oxidation via dynamic electrocatalytic modulation. That's a lot of words, Omar. So what does that mean?
So the basic idea there is when you apply a potential to facilitate a Faraday chemistry, it's hard to balance both your kinetic needs and your thermodynamic needs for a catalyst. So the idea is instead of trying to find one voltage or one set of material that can satisfy both, we would instead oscillate between two distinct potentials, one which favors kinetics, another which favors thermodynamics. And as a result, you hit a pseudo steady state that satisfies both of those needs better than just a static applied potential.
Interesting. And so when you say thermodynamics, just for the lay people like me, so you're talking about the adsorption step of the formic acid coming onto the platinum?
That's right. The adsorption step and the coverage of other relevant reactive intermediates. You want to be able to have sufficient coverage of them to get a higher rate of reaction. But doing that tends to sacrifice the value of your kinetic rate constant.
Okay. So you kind of go to these low potentials, which, for lack of a non-scientific word, but sucks up the formic acid, kind of gets the surface coverages you want, and then you ratchet up the voltage to push the reaction forward from those surface intermediates. Is that more or less correct?
In a sense, yes, that's exactly it.
Okay, awesome. Well, so what made you? I understand that this dynamic catalysis was invented, at the University of Minnesota while you were there. You and Paul Downhauer, and is pretty new in the field. What made you choose to go this direction?
I think what made us choose to go in this direction is that there's been a challenge for quite some time in the field of heterogeneous catalysis with how can we design more effective catalysts, and the focus has in large been on materials design, which is kind of facing an upper bound on what material design alone can do. So this was born sort of out of necessity and trying to accelerate the rate of many important catalytic reactions and realizing there was an entirely unexplored dimension, which is essentially time.
Yeah, it's pretty cool. Well, what did you guys conclude from this work?
So what we concluded is that even with simple off-the-shelf catalysts, which don't require any exotic synthesis, aren't highly expensive, one can significantly increase the rate of a reaction by orders of magnitude just by virtue of energetic oscillations. So moving away from steady state operation, but only at the catalyst layer where you are applying energetic oscillations, which makes it a manageable form of reactor operation that you can significantly improve the rate of an existing catalytic system.
Wow. So this has ramifications in every area of catalysis. And do you think this could be applied in all those areas, or is there some barrier because of the need for oscillating some electronic property?
Yeah, on the surface, it seems that any heterogeneously catalyzed reaction, it's worth considering. Can you operate it in a dynamic sense? And all what it really comes down to is, can you find an energetic stimulus that your catalytic chemistry is sensitive to, that you can apply reversibly to the catalyst surface on time scales that are comparable to that of the catalytic chemistry? If the answer is yes, it's definitely worth exploring whether you can operate your system dynamically.
Interesting. And so that time scale piece is pretty important. You're oscillating at a time scale that's relevant to the turnover frequency, is that, or is it to the sort of adsorption events?
It's a little bit of both, yes. So essentially, you want to oscillate your surface at a frequency that is faster than what your catalytic surface can re-equilibrate. So if you go too slow of an oscillation, or with too slow of an oscillation, your surface says, I don't really care about what you're trying to do. I can re-equilibrate and hit those same steady state coverages. If you go too fast, it's kind of like a hummingbird flapping its wings with the human eye. Your eye can't process the image fast enough, and it looks static again. So there's a sweet spot in the middle where you're oscillating at a frequency that matches the natural turnover frequencies of the catalytic material.
I see. Very cool. And then, of course, I assume you still got to worry about mass transfer. So you can improve the catalyst a lot, but in a lot of these reactions, you might need to still worry about mass transfer limitations.
Absolutely, yes. As you start to increase the rate of reaction, you have to worry about whether your products can diffuse out of the porous network fast enough, or whether you can replenish the catalyst surface with reactants fast enough from the bulk phase. And that's part of why in the first experimental demonstration of this work, we chose to go with a non-porous system. Yeah. Just focusing entirely on what's happening on the catalyst surface. And then later in subsequent pieces of work, adding back that complexity of a real catalyst.
Well, I love the simplicity of what you guys chose, a platinum wire, and you can just oscillate the voltage there and look at formic acid decomposition. That's very cool. So could you then take an iron wire, which I assume is 1,000 times cheaper than platinum, and could you repeat the same experiment and maybe get rates that are similar to platinum at steady state?
Yeah, you've hit the nail on the head. That's exactly where we want to go to and are currently working towards, is how to now take cheaper metal catalysts, iron, maybe the coinage metal like copper, and if we can even get them to catalyze reactions at a rate comparable to precious metal catalysts, that could be really revolutionary, because we wouldn't need as many of the precious metal catalysts as we did in the past.
Yeah. Oh, I see a ton of ramifications. So ammonia synthesis or hydrogen synthesis or any of these large reactions that we do with either precious metals or at conditions that are expensive. You think this could disrupt a lot of that?
Absolutely, especially in cases where you have high pressure reactions, which can be a killer for many process technologies, particularly when you attempt to scale them down. If we could increase the rate of reaction just by virtue of these energetic oscillations at a cost that is significantly cheaper than the cost of pressurization, both on the capital and the operating side, we think this could make a significant impact in those areas.
Wow. Have you looked at like poisons? And I assume if you had a sulfur bound to a catalyst surface, you could change the voltage to push that sulfur off. Are there ways to, I'm thinking about hydrodesulfurization or other sulfur sensitive reactions. Could this approach be used in those cases?
I think definitely so. If you can find an energetic stimulus that can affect the strength with which sulfur is binding to the metal surface, or how fastly one can, let's say, oxidize or reduce the sulfur off the surface, that can definitely be applied. In the case of formic acid, we had an analogous situation where for the longest time, formic acid decomposing to carbon monoxide in these electrocatalytic systems was considered a poison because you couldn't quite get it off the surface, even though you could decompose it to carbon monoxide quite rapidly. We found that if you oscillate the surface in terms of its applied potential, you're actually now accessing that route of formic acid completely decomposing to CO2, but through the carbon monoxide route, which was previously considered a poison because you couldn't complete the turnover.
Oh, interesting. So you're accessing a new transition state, essentially.
Yes, it's steering the pathway selectivity towards the same end product.
Yeah. Wow. Well, tell me, since we're an analytical company over here, tell me a little bit about how you did the analytical piece of this, how you measured your components and how you decided what to do there.
Yeah, so the major challenge we faced, for the reasons we were discussing earlier, the desire was to work with a platinum wire. The challenge there is you have a very small number of active sites, and that translates into relatively low concentrations of our product, in this case, carbon dioxide, which we needed to quantify. Traditional analytical techniques like a gas chromatograph equipped with a thermal conductivity detector, or even a methanizer, were challenging to use due to sensitivity limits. So instead, we realized when looking at ARC's catalog that we could simply use a jetonizer, which was appealing because it was cost effective, very easy to add on to an existing GC system, and gave us very high sensitivity towards carbon dioxide by virtue of now having a flame ionization detector that could see the product essentially. That really allowed us to quantify ppm, at times ppb levels of CO2, which is what made this research possible to get that chemical or analytical chemistry certainty when quantifying our products.
Yeah, so you were using GC coupled with jetonizer FID to measure CO, CO2 with some sort of carbon column, or what was your column choice? Do you remember?
We were using a plot Q column. We were trying to get anything that could hold on to it quite some time and separate out CO and CO2.
Yep.
So it worked great. We wanted a capillary column. We didn't want to dabble too much into micropact or cryogenic separation. Yep. So that worked out nicely for us, and we could quantify CO and CO2. And the added advantage of the jetonizer is we realized they both had the same calibration factor. Since they're both turning into methane, which made our life on the analytical side much easier.
Yeah, easier than TCD for sure.
Yes.
Cool. Well, did you? I guess what's the follow-on with this work? Where are you going to go next? And analytically, are there any differences that you would choose in the future?
So where we're going to next now is working with more complex reactions. Complex in the sense we now have a challenge of product selectivity, not just pathway selectivity. So we're looking at more relevant electrochemical oxidation technologies that we can now try to control the oxidation selectivity towards value-added products. And there we're going to have a much more complicated mixture of products where we're going to be using something like a polyarc device because we have more than just CO and CO2 to consider.
That's awesome. Well, you'll have to start looking into hydrogen electrolysis too and see if you can do this. And then call me when you make your first $1 billion.
That's the dream. If we can get those water electrolyzers to speed up without having to use something like iridium oxide or platinum for your cathode and your anode, that would be the dream.
Any work in that area from your group, or is that future?
We hope to get into that space in the future, maybe not just with applied potential oscillations. So they're simply oscillating the applied potential may not do the trick, but there are other strategies, other forms of energetic stimulus we're looking into that we think can make a difference. In particular, we're looking into where do you need help? Is it on the cathodic side of the reaction or the anodic side of the reaction? Trying to be targeted in that sense.
Yeah, that's smart. Well, excellent. This has been fantastic, Omar. It's always fun to learn more about this topic and kind of see where the future is headed. You're definitely forging a pretty cool path here, and I'm excited to see what comes out of it.
Thank you very much, and it's always great talking with you, Andrew.
Yeah, thank you, Omar. Well, take care. Good luck this semester, and yeah, don't be a stranger.
Thanks. Same to you.
All right, thank you. We'll take care.
All right, take care. Bye.